Morning, and we have with us today Dr. Srijit Paul from Hadronic University. Srijit did his PhD in Wuppertal University. It was a joint position, Wuppertal and Cyprus. And then after postdocs in Mainz and Edinburgh, now he's been a postdoc followed it up at Maryland University, Maryland Center for Fundamental Physics for a year now.
Yes.
So he's going to tell us about G-2, the muon, anomalous magnetic moment, and lattice versus data-driven new physics.
Yes.
Okay. Yeah, you have to tell us what.
Yeah, exactly. So, thanks for inviting me. Thanks for inviting me to give me the opportunity to give a talk on this topic. So, today I'm going to talk about the muon, anomalous magnetic moment of the muon, and there have been predictions from data-driven approach, the dispersive approach, and also there is a part lattice calculation approach, and there have been some drift between those numbers, as you know, recently, and based on that, there have been lots of new physics proposals that have been proposed. And today's talk will be mainly first starting with the lattice approach to the hadronic part of the G-2 physics, and it will basically elaborate the results that are obtained from the Mainz collaboration. And following that, we'll discuss possible new physics scenario that we tried investigating with the group in Maryland towards resolving this one. Okay, so let's start very first on a very toy introduction to how you go about measuring magnetic moments in experiments. So actually, I had some kind of animation, but then here the PDF version, I will just show you if I have a charge particle with a spin S and velocity V, and we are familiar with the cyclotron being a magnetic field inside, and this will basically move the particle around this cyclotron ring, and because of the interaction of the magnetic field with the charged particle, there will be a helicity flip transition. So what's happening here is the spin projection with respect to the along the velocity v will start to precess, and what measures is the frequency difference between the cyclotron frequency and the longer precision frequency that happens, and that should give you the omega a, which is the difference, which is called G-2/2. So if there was no G-2, if G was exactly equal to 2, then you basically have both the frequencies to be equal. But here, omega A will be determined by the exact determination of the charge d of the particle, the magnetic field, and the mass of the particle. So if I know these three quantities to very high precision, obviously I haven't written down the relativistic effects of this. There are some extra corrections. So this is the typical way of how one goes about measuring magnetic moment of a charged particle. And this has been successfully established in experiments in BNL, Fermilab, and JPOT is supposed to start. So once I go about magnetic moment, let's talk about this part. So back in 1928, if you just use relativistic quantum mechanics and start with the Dirac equation.
So you have in your previous picture.
Yeah.
Yeah. So if I understand you correctly,
Yeah.
There is a spin B coupling between spin and B.
Yeah.
And that causes the spin to precess. Because the charge particle itself is going around in a circle.
Okay.
So these two frequencies theoretically are expected to be the same
if G is equal.
But when they are not the same, it shows up as the difference between.
Okay. This is what they are trying to measure in experiments. And okay, so if you just start with relativistic quantum mechanics with the Dirac equation, and then you try to write it, the interaction term as mu dot b, you will soon realize that in the mu dot beta, your G has to be equal to 2, which was the point of action given back in 1928. And then as time progressed, people realized that this is not the correct picture. One needs to include the relativistic and also the quantum field-theoretic approach towards computing. QED approach was devised in 1948 by Schwinger, Feynman, and Tomonaga. So back then, Schwinger computed the first order correction to this particular uh, diagram, and this was just the virtual photon being exchanged between the two muons, and here between the same muon. And then this correction was computed up till first order, and the first correction comes out as alpha over 2 pi, so which comes out around 0.00116. So this was the first correction that was proposed back in 1948. But as you can imagine, this is just a first order effect, and one can actually go about computing this quantity to much higher precision, including all the higher loops, in this case, the QED loops. So now let me just focus on why do we need to study this particular quantity? What is the first place? So in the standard model Lagrangian, this particular quantity or this interaction that we talk about, when my muon is interacting with the photon, is not exactly this. This is a 5-dimensional operator. So this is not a part of the Lagrangian itself, because then we know that our Lagrangian is renormalizable and it cannot have a 5G operator in it. So this comes up as, so at P level it vanishes, does not have any contribution. So it's not a free parameter of the Lagrangian itself. So that's why this is a more unambiguous theoretical computation that is possible within the realm of current model, so that we can test correctness of it.
The A here is the same as the
Yes,
other.
A is here also, and lambda is the scale of sin. And this helicity flip transition is actually proportional to the mass of the particle that we have. That is related to new physics scale called M. And here, the relative precision on the A is proportional to the scale of new physics where it can appear. So this basically can act as a sensitive parameter towards testing all the new physics that are possible within the data. So, and in this case, because the muon is proportional to the mass of the muon, and muon is heavier than the electron 200 times, and that's why it becomes more sensitive to the presence of any new physics that can appear in our world. So this is almost 10 to the power 4 times more sensitive to the to new physics compared to electron. One might argue that you could have used tau. Tau is it's more unstable, so it's more difficult to detect experiments compared to muon. So this is one big motivation because it acts as um, a ground for testing the standard model Lagrangian to a very high precision. And the precision that I am talking about is actually 10 to the power minus 11. And why do I say that? Because if I look at just the AMU standard model, it can be decomposed into 3 different parts: the QED contributions, which is due to Kinoshita and company. So they have computed this up till 5 loops to very high accuracy, and you can see the precision is 0.001 parts per million, which is a very highly precise value for computation. And then they have also computed the weak. The details you can find in the theory white paper back in 2020. So the weak has also been computed at 2.01 parts per million. But the biggest uncertainty that is coming in the overall prediction of ABU standard model is coming from the hadronic part. And the hadronic part, which I mean, is that the virtual photon that is being exchanged between the muon can actually lead to production of quark antiquark pairs. And that's what this blob is all about. And this has uncertainty which is 0.37 parts per million. And that's why this is one of the prime reasons why we're going to talk about particularly this AMU HVP, and we'll try to understand how can we uh, make this prediction more precise. Today, also there's a line by line prediction, which I won't be talking about, but you can see the most uncertainty is actually coming from the HVP part. So today's talk will be basically focusing on HVP part, but one should not say that HVP has a huge role to play in AMU. AMU has the highest contribution from QED effects because it's a QED interaction in the first place, the tree level, and then now let's see how does one go about computing this particular blob, this quantity. So this is the quantity that we are interested in. And this can be, this was shown in 2003, it was shown by Tom Blum that one can write this integral in a very clever way, saying that this integral is itself a finite integral and can be Wick rotated, and the external momenta part can be again rotated back, but this extra photon part, which is just dependent on the moment of the photon, can be separated out. So this particular integral can be written as two parts. One is here the FQ square, which I denote as the the electronic part, which has the muon in it, and then you have the hadronic vacuum polarization part, which is the pi. So pi is, you can see, you can imagine that this is an electromagnetic current which is creating quark antiquark pair. And then you have annihilation operator, which is destroying the quark antiquark and giving back the photon. So this basically entails towards, if I can just compute this particular matrix element with the current, then I'm actually done with computing this particular quantity. And this was shown by Tom Blum that this can easily be computed if I am only in the space-like domain. So Q square is in the space-like domain. One can compute this. So this is a typical integrand that I'm talking about here, FQ square and the pi Q square part. So one basically needs to compute the area under the curve. That's when one can compute the mu HVP. So uh, this is the starting point of how does one go about computing this quantity. But then obviously there are different approaches towards this particular integral itself. And the two known directions that people already know, the dispersive approach and the lattice method. The dispersive approach can basically mean that if I have this hadronic vacuum blob, I can write it with the help of optical theorem as the mod square of the E plus E minus 2 hadrons information that comes from experiments. And so this particular approach, dispersive approach, has this quality that it can give you a channel-wise information about whether I have 2 pi contribution, 3 pi contribution, 4 pi, and so on and so forth. And all the different channel contributions can be easily isolated out using this.
How do you shape ions? Do they have to be on shape?
The ions here are not on
Just be quarks.
Yes, they're quark antiquarks. The lowest one, because you have this S square in the denominator, you can think of this, the low energy part is getting weighted highly compared to the high energy. That's why you have the lowest energy, the lowest mass meson contributing 556 contributing more than the higher mesons. So this is the reason why there is an more effect of the non-contributing part of the QCD E plus E minus 2 hadron spectrum. Because I'll be showing up the E plus E minus 2 hadron spectrum, you'll see that the low energy part has all the non-contributing effects with the resonances coming in. And so in principle, that is difficult to take into account from first principles. The reason why one resorts to taking experimental input and then computing the area under the curve. And the next approach, which is the lattice approach, what it basically does is instead of going over to E plus E minus 2 hadrons, it directly computes the current correlator. And here also it was proposed back in 2011 that one can write this integral as an integral over dt, where k tilde is analytically known QED GT is what we call as lattice input in this. So GT is exactly the current correlator. And so why is this? This is a completely different approach than what we had, but this gives the same quantity, which is HVP. And the reason it's completely complementary to what we had here was this is not a direct experimental input goes into computing lattice calculation, and also this takes into account the non-perturbative effects. And another important feature is one can actually, as you can see in the current, there are different flavors. So one can actually look at different flavors separately and the contributions separately.
Do you
And
have any experimental result?
yes, I'm going to show you this. Yes. So these are the two complementary approaches towards computing the gaming HVP. And as you asked, are there any results from experiments? Yes, there are. So until 2021, there was this picture from the white paper that I have shown, that I'm showing here. So this is the BNL plus the Fermilab result.
About the hadron mode.
Yeah, hadronic mode. So basically, if you feed in the hadronic mode, you get these 3 points. So this I will show you exactly. So this is the E plus E minus hadrons, right? So one takes into account this area under the curve, and sigma directly goes into. So the experimental value, the more uncertainty you have in the sigma, the more difficult it is to compute the AV. So I'll come to this in a moment. Just hold to your horses for a moment. So what I'm talking about here is we have the experimental value in 2021. Formula had just released their new G minus 2 results. And if you just take an average over BNL and formula results, you get this yellow band. So here it is denoted by 0. And then at that time, we had some dispersive approach results available where they have taken into account the E plus E minus 2 hadrons from experiments like Babar and Chloe. And they have computed the AMU HVP from data driven. And these are the points, the red points that you see here. These are the points that they obtained. And then if you look at the lattice results, the lattice results are this blue band that you see here from different collaborations. Back there, 2019, you have ETMC, Mainz, RBC, BMW 2017. So this had huge uncertainties back then. And I'm going to discuss about why the uncertainties are coming about and how do we go about
the error was.
Yeah, so this is just to show this. This is the standard model, this value. This is the experimental value. And this is where the lattice, the BMW result is. So it is somewhere in between. Just to show you something out of that.
Lots of the points are before 2020. Is it?
No, this is 2021. So 2020, they released, BMW released their first result. Right? So they were somewhere here. But you can see that that time they released the full lattice result. But then there are some uncertainties related to that, which I will discuss. But then again, in 2024, things got a bit more murkier, I would say, as CMD3 published their new results, and Fermilab also came up with their experimental results with 2 more runs. And if you take their world average, then this is the pink band that you get from experiments. And now, if I take into account the sigma hadronic cross section from the CMD3 result, which is 2401, if you take their result, just their pi cross section result into account, then you will see you get a point somewhere here, which is the gray one. And if I do not take the CMD3 result by the Russian group, then I have this point which already has a 5 sigma difference from my experimental value of 3 minus 2, right? And if I take this CMD3 result and also take a global average of some sort of all the experiments, then also it's quite far from the standard model. But if I just take the CMD3 result, then I am down here. So this is the reason why things are getting more murkier, and the reason why CMD3 got such a huge value was because their pi plus pi minus cross section was actually 5% higher than all the other experiments that published their results, Babar and Chloe. So what I mean by that is basically this cross section that was published So especially the pi case that was published by CMD3, which is the rho omega here, in the 600 to 800 MeV region, they had a higher cross section compared to the Baba and Blue. So obviously, this is the reason of all the controversy right now that why things are not in place. And I think there have been an IIC contribution by, and I think back in 2020, where one can basically write a new pi contribution as in terms of the pi and form factor, and then there is a way to relate the pi and form factor with the phase and get a prediction for the AU by pi in this regime. So this was the dispersive relation approach. Let me talk about the lattice approach. How does it go about lattice computation? So AU HVP, if I just take the current correlator and if I try to compute it on the lattice, and so basically this is the G x naught, and this is the QED curve. So in this particular integral, if I perform, and if I just plot the integrand, because integrand is what will give you the AMU HVP. If I just plot the integrand, I will get a plot like this. Now, what does this mean? This is basically saying that if I try to get an area under this curve, I will get huge uncertainty from the tail of this particular plot, as you can see here, which we call in lattice context as a long distance contribution towards the ADU-HVP. And there are several challenges towards computing this particular entity on the lattice, because you can see there's an exponentially growing signal to exponentially decreasing signal to noise. So the signal is decreasing, but the noise is growing exponentially as x naught goes to infinity. And then obviously, because we are in a finite box, there will be effects on the finite volume box itself, and also the lattice spacing effect, the discretization effects, and discrete diagrams, and isospin breaking effects. So all these things will get clearer when I start to talk about the lattice setup itself. So this is a typical error budget that one comes about. If you look at this, the light contribution has the highest effect towards computing this particular quantity. So that's why I'm looking at only the UD, the light cost in this particular. If you mean by. So, okay, this is how a typical lattice calculation goes about. So if I'm talking about a particular observable O, and I want to compute the average quantity of this observable, what I mean, this is a language from StatMech that you must be familiar with, is what I do is I have a certain probability with which I generate U are the gauge configurations, basically gluonic configurations, right, on the lattice. And with this probability, if I generate all possible paths that can happen in for a particular interaction to happen. So if I am trying to, if I generate, so what is happening in a typical lattice calculation is we generate configurations with this particular probability density, and as you can see that the Z is intractable. So that's why people resort to Monte Carlo methods, Markov chain Monte Carlo. With this probability, they generate gauge configurations U, and for this simulation, people need supercomputers of so typical lattices are of the size of 64Q or 48Q lattice. And so once the lattices are generated on supercomputers, the next approach is this particular observable will be a function of the Dirac propagator, which is the inverse of the Dirac operator. And Dirac operator itself has some quad mass dependence in it. So uh, the more lower the, so D is a function of NQ. So D inverse will be naturally a function of NQ inverse. And so lower and lower quark mass, the more difficult it is to invert this particular matrix. And that's why people resort to all kinds of computational methods called multigrid, one of the state-of-the-art methods developed to compute the propagators. And using this, once you have the propagators, the next thing is on the lattice you compute the contractions between the different propagators. So if I'm in this case, suppose I'm typically constructing a proton here. So I have a creation operator and I have an annihilation operator. So I have the propagators connecting both of these. These are all possible big contractions that can happen. This is one such toy example I'm showing. So you basically multiply the propagators, big contract propagators here, and then one gets correlator. And once you have the correlator, you have an observable for every gauge configuration in your simulation. And then one does just simple data analysis, just the mean variance of this particular quantity, and one obtains the observable. So this whole setup is being performed using importance sampling, so one does not need to actually uh, consider the whole distribution, but only where the probability is very high of sampling. What to say is, so Edison, these are also for computers, Corey and Edison. These are all machines that I've been using in my research. So yeah, these are US based. Edison has already retired. So Corey is the only one that's there. And this is the German machine where Jewish. So once you perform this mean one obtains, so this is the typical lattice one observable that I'm talking about. It's just baryon masses. If I just take the proton, I do the correlation function, I extract the mass, and the mass step. So once you have the observables, this whole setup is then repeated towards, because as I say, lattice is a systematic way of dealing with uncertainties. And the uncertainties are basically keeping in from the box size. So as you grow the box size, the quantum effects can be taken into account. And then you have the quark masses themselves. You might have seen that most lattice calculations happen at a much higher physical fine mass. So people try to again decrease the quark masses so that the fine gets more physical. So this is the m going to m physical limit. And then you have the lattice spacing itself going to zero. So the L tending to zero will tell you something about the UV physics you're trying to work. The A tending to zero will tell you something about the infrared physics or the high energy physics, basically, right? Sorry. So high energy physics is basically the A tending to zero, which is the UV physics, and then the low energy is infrared physics, which is the box size. And then you have the chiral behavior as you go to more and more physical quark masses. So these are the three different systematic errors that any lattice calculation should take into account.
Is there a picture like that for the mesons?
Yes, there is.
There is a picture.
Yes. Okay, so this is a typical hadron spectrum, how it looks like. So whenever one goes for computing a particular operator, correlator. So this is, for example, a pion. So you have a continuum quantum number operator, which is O and O tilde. What one does then is on the lattice, because you are in the lattice, we can always insert a lattice tower of states, because on lattice you only have uh, discrete energies, you don't have the continuum. So you can just insert the identity operator here inside, and then you just look at the overlap of the operator on the lattice tower of states. So what you end up getting is basically sum over overlaps the z functions and corresponding energies on of the lattice tower of states. And then what basically says, so if I take it to the infinity limit, what remains is only the ground state. So this is a very typical lattice calculation where one goes. So basically, what one sees, the limitation here is you can see that this particular approach is only possible if I have an isolated single hadron state that I'm interested in, and it's a QCD stable state, it's a ground state. In all these cases, this particular approach works out beautifully, and one can see that here for the nucleon. So you can see that things which have some width which are not stable on the lattice, you have a huge uncertainty associated with those particular values. The same case can also works for mesons, where you have uncertainties associated with decaying particles. So obviously you can see that this does not work very well for excited states, right?
What are the typical errors? Around 10%.
Depending, so there are some observables which are up till sub percent, less than a percent. So also the G minus 2 calculation that I'm talking about is going to be sub percent prediction.
No, I mean just
Yeah,
but I can see that many of the other ones are
yeah,
20%.
exactly. So basically the things which have a bit, because delta is not a QCD stable state, right? So delta will is if you just do this approach for delta, you might get a huge error in your mass, so which won't give you anything reliable to work. And people have come up with more intelligent strategies to deal with excited states on the line, which I will discuss now. Okay, now let's come back to again our observable of interest, which is the mu HVP. And I'm interested in this particular quantity, and I can see that this also has a huge uncertainty in the tail. So, what people on the lattice have done is they have come up with clever methods to split the effects or the systematic effects that can happen in our integral. So if this was my integrand, what we have done is we have split them into three different sections. The first one is what we know that is mostly affected by discretization effects or the UV effects. And then you have the finite volume effect, blue part, which has all the most uncertainty coming from. Right? So what people have done is these three are called windows in Latin, or now it has also been accepted nomenclature in the G minus 2 community that the integrand itself can be composed into three different windows. This is the short distance window, this is called the intermediate window, and this is the long distance window on the lattice. And the reason behind splitting them is because all these three windows have different systematic uncertainties that can come out. That comes up. So what here what I'm showing is this integrand now for the long distance part. That's why I noted by blue. The long distance part is by vector based on dominance inspired reconstruction. One can write the current correlator as being populated by just the pi states on the lattice, which are the lowest lying states on the lattice. So what one approach is just take the current correlator and compute the overlap of the current operator with the pi space on the lattice, and that should give you enough saturation for the long distance part. But then there is another approach. The problem is this will still have finite volume effects in it because pi states itself are also computed in finite volume. So they will still have finite volume effects in it. So in order to take into account of this finite volume effects, what people have done is they have tried to map. So on the lattice, there is a mapping one can do from finite volume to infinite volume using Lucia quantization condition. And then one can basically write this quantity in terms of the fine, the time like fine form, which is f fine. So that particular quantity gives you another way of computing this, but this has no finite volume effects, or they have been controlled. So these are two different approaches that I will talk about on the lattice. So now I will just move on to a typical lattice calculation. So this is the lattice setup that I have in my calculation here. So what we have is we have a physical point lattice. So we have a point which is at the physical point. The box size is 6.2 Fermi. The lattice spacing is 0.06. And obviously there are no thermal effects because our M pi is 4.2, more than 4. And so once I have configurations generated, which is for this lattice box 96Q192, and this is the gauge action that I chose. So the idea is we will construct pi states, pi elastic states within the region 0.25 MeV to 1 GeV, because I know in this regime my long distance part of HVP correlator is getting saturated by pi states in this regime in the isospin equal to 1 cm. So this is isobatic. So what I am going to do is I'm going to construct all the pi states possible between this energy range, and then I will try to look at overlap of my current operator with these pi states. And that's going to give me, so the hypothesis is the pi states are going to saturate towards contributing to the current. So what I mean by that is, so this is the typical hadron spectroscopy pi correlated construction. What one goes about is construct this pi states on the lattice, creates them and destroys them in the isospin I equal to 1 channel. For this region, I am looking at the momenta from 0 to b squared on the lattice. And then what this basically entails to is constructing rho-like and pi-like operator in this. These are all the big contractions that one does on the lattice. And this basically, I just did a small estimate. If I want to do this on an ISC provider, this would entail using zero 0.8 GPUs, which is 80% of the GPUs for 2 months, and I will have this calculation. 80% of, so there are 80% of all. So there are 80 GPUs, V100s, and if I do a 64 GPU calculation, I can do this within 2 months. This particular calculation can be, this contractions can be. And then once you have the contractions, one projects them into the relevant event, because on the lattice you don't have all the symmetries that you want in the continuum. You have a discrete set of symmetries, and that's what you need to project. And then you extract the spectrum, and then you reconstruct your current. Now, what do I mean by that? So this black point was my current correlator, and then I have different pi states, right, which I can construct on the lattice. So these are the different pi energy levels. So when there is back-to-back 1 unit of momentum, back-to-back 2 units of momentum, and 4 units, so you can see that up till 4 units, I have saturated the current correlator and the tail of it. So all the uncertainty that I had in my current correlator, which was contributing to my AMU HVP uncertainty, right, is being taken care of. So what this has basically done is this has actually given you an exponential noise reduction in the tail. So this was my previous AMU HVP prediction. If I use the black points and I was getting this, you would see that most lattice calculations before 2020 had huge errors. So that is basically coming because of the tail and because of this exponential noise that's there in the tail. And then using this pi states, one can get an exponential noise reduction in the tail. And using this approach, if one goes about computing the AMU HVP,
how was it done again? How is it done now?
So back then, one was just computing the current correlator itself, and so basically this integral. And they were now what we are doing is instead of sorry. So you can see up till around 1.8 femtometer, this noise is very small.
And I just want to know what's the difference in the technique.
So technique is, yeah, up till 1.8 for me, they were taking the current correlator. And after 1.8, they are doing just the pi states. Okay. So instead of taking the current correlator all the way, so earlier they were taking all the way current correlator integrand. Now they are saying that we will take the current correlator.
Blue points are pi.
Yeah, blue points are pi.
So that's the better technique. Blue is the better technique.
Correct. So this is an approach that I ended in 2023 with the Mainz collaboration. And I think Mainz was the first collaboration who did this kind of approach towards taking care of the tail.
So looking at pairs of ions being produced is
exactly,
at least in spirit more like the dispersion relation approach. Because that's
no, because they're in space life domain, they're not in the time life. So you don't have all these features of
you may go to the space life region eventually, but
yeah,
as far as the computation is concerned, you look at pairs of ions, pairs or
you can go to 4 points here. So you're looking
that's how you would normally think of.
This is true for literally any observer on the lattice at longer distances.
Yeah.
Will be saturated by the low line states. And the low-lying states for the lattice QCD approach always are high.
But if I understood you correctly, they were not doing it like that.
Yes, they are not doing that.
So,
Because multi-hadronic states, this approach, computing multi-hadrons from the lattice. That
at least the way I understand dispersion relations is that these would be the low-lying states would be the leading contributors. And I didn't need to know lattice case theory, just from the theory of dispersion relations.
Yes.
These are, so if I understand you correctly, it is by incorporating in spirit the approach of dispersion relations into lattice calculations that you have significantly corrected errors and error.
Yes. But there are some issues in dispersion approach where you have this omega going to 3 pi. Here you don't have to worry about all this. Only pi in the lattice. Because that's
When you say you don't have to worry, do you mean that you didn't worry and you got the.
So if you compute them, they have already, the pi states have already saturated. So if you even if you take the 3 pi, they will basically fall on top of.
So they are not going to give you a further improvement.
Exactly.
So that is the point.
Yeah. So dispersive approach is giving you a motivation in some sense. Why do we need
And
to
also that some particular process is contributing less or does not even help you improve is a separate point.
Yes. So what I also on the lattice, as I said, one can compute the transition format and also the phase shift that one goes about. So the typical approach when people try to go about computing a dynamical quantity on the lattice is through something called Lucier formalism, which is basically telling you a mapping. So what one does is in different frames, moving frames and center of mass frame, one computes the spectrum on the lattice. Right? This is the spectrum that, and it is typical in this. This is a very toy picture. You have the spectrum, and these are the non-interaction states, the non-interacting pi states on the lattice. So once you have the non-interacting pi states on the lattice, because of the interaction between pi, the rho that is happening in the pi states in the I equal to 1 channel, you have a slight energy shift on the lattice. So you get a delta E from the lattice. And the Lucier formalism tells you how to map these energy shifts directly onto the dynamical quantity, which is the phase shift. And I'll show you an example. So this is our result for the pi phase shift with the physical part in the I equal to 1 channel. So what I'm showing here is the scattering phase shift, the center of mass energy, and the orange and the blue points are the experimental points from experiments from pi side. And the blue points that you see here, the dark blue points, these are the lattice results. And this gray band that you see, because I tell you that lattice is a statistical approach, right? So there is a resampling technique that is getting involved when computing a Monte Carlo calculation. So these are the different resampling bins. So if I compute this particular energy for different bins, I get a spread. So I get every point is a Gaussian. So this is the Gaussian that you see every point. And this is, you can see that it qualitatively almost matches what we have in the experiment for this calculation.
So the red and blue circles are experimental data.
Yeah, it's the blue circle.
And then the square is lattice data.
The square
the
is
gray points are also lattice
Yeah, the gray points are basically the spread of so the mean is the blue points, and the spread of the Gaussian or the resampling, the bootstrapping sample. So we have around 1,000 bootstrapping samples. So if I just compute this quantity for every resample, then I get this spread, all the points. And so basically the mean of that sample is the blue, and the spread is.
Why are they diagonal in some cases?
Yeah, because this technique mapping from finite volume to infinite volume is a nonlinear process. So which involves computation of zeta functions, and that's what makes it, uh, you know, you can see that there are the errors grow as it goes higher and higher energies, and this shift that you see here, because this every bootstrap resampling is being computed So what I mean is there is a tan inverse involved. And a tan inverse basically will give you a skewed picture instead of straight line. That's why. So once you have the scattering phase shift, then one can go about computing. This is a very preliminary result that we haven't yet published. This is just the F5. And these are different parameterizations that one tries to fit for them. And the gray points are still not taken into account. They can still be taken into account. We are still processing this data. This is still under process. But one can see that one can actually fit some parameterizations that are possible on these blue points for the F5, which can then go into computing the HVP. So now the
largest value of I forgot the exact of data.
yeah.
You have large spreads, but how is it? Kind of curious how your mean value is still very close to the red.
So there are actually 1,000 points for every point, and there is a huge density of points around here, and there are some points coming out here. So this is
Picture is not telling the full story.
yeah. Basically, you can think of this that so whatever spread you see, the big error bar, one sigma, right? On this.
There are zillions of points.
Yeah. Every point has 1,000 points. So this is just to represent the uncertainties that can come up because this computation involves computing this quantity for every bootstrap sample. That's itself, and each of them is giving you some uncertainty, but they are all getting concentrated on these blue points. That's the beautiful picture that emerges, and one can see that spaceship comes out naturally. And then one gets the F5 out of this. And then if I go about computing HVP for the whole, so this is again back to the first picture that I had. The experimental value is the orange band. And this is the E plus E minus 2 hadrons band, the dispersive approach band. And then our result for the Mainz collaboration is up here. So this is the latest result that's come from the Mainz collaboration. So as you can see that the error bars have contracted substantially compared to what was earlier the Mainz result, right? So this have so earlier lattice was the method which has to take a side. Now either it was going towards dispersive approach or the experimental value, and clearly lattice has chosen the right one, the right approach. And so this again has led to a puzzle in itself. That why is the data-driven approach lower than how much it should be? So this is what we call as the HVP puzzle, hadronic vacuum polarization puzzle. And this is of the order of 10 to the power minus 11, 210. So this is a negative value because this is lower than how much it should be, right? So the idea is what contribution can lead to an E plus E minus 2 hadrons being a lower value than how much it should be. So some of the conjecture that me and my collaborators back in Melbourne, X is the new physics, basically, yeah. So this is one of the so one way to think about this is E plus E minus 2 QQ bar. This is the simple picture that we have.
But when we do this in E plus E minus 2 lighter, there is no X. We know that it's either gamma or G. There is no X.
Yeah. So I'm saying that how would you go about detecting if there is an X? It will be giving you a lower value of this kind of intersection. I mean,
Yes,
when
the
you
physics module to account for the lower cross sections.
yes.
But even that doesn't make sense because CMD is seeing a higher cross.
Exactly. So I'm just suppose we are in a pre-CMD trial because right now that still is making picture a bit murkier. So I'm saying that if we try to, we can write an amplitude. So what we measure is the QQ bar, right? In experiments. We don't see the photon as such. So there could be a new particle which can also give rise to QQ bar, And so what you will end up getting is finally the sum of these two effects in your detectors, right? We measure pi plus pi minus for sections, but then the pi plus pi minus is coming from the photon or coming from an X, you don't know. Right? So what we are trying to propose here is that there could be a negative interference because these are two complex amplitudes. So if I try to add two complex numbers and take a mod of it, I'll get an extra interference. And this is what we are trying to make money of, saying that this could be pushing the value lower than how much it should be. And what in the next slides I'm going to talk about is what are the different.
Then your explanation of this,
Yeah, that depends on new physics. Yes. So then it would say that if I take into account, if I remove this new physics, then I get a value which is here. But the reason why we are getting a lower value is because this contribution is pushing it low. So what in the next slides I'm talking about is what are the possible new physics scenarios that I try to explore with my collaborators.
the CMD3 result is not correct.
So this is one scenario. You will see that we have taken into account CMD3 as well. So one scenario, just for the sake of brevity, I'm talking about these two models, baryon number gauge boson and dark force. And so this is basically QQ bar with a B being extra generated. And here the coupling of the new physics with the quark is much, much higher than the coupling with the lepton. So this, and then you have just the coupling with the dark photon. So if I take these two approaches and I try to, so what we are proposing in the paper, this 2412 paper is any new physics has to pass these two tests that we have proposed. One is called AMU test, one is called AMU HVP test. These are saying that if I say that there is any new physics, it would actually directly contribute to AMU itself, right? Because you have a QED contribution, you have a Z contribution, you have HVP contribution, and you also have this synthesis contribution. So if I'm trying to solve this puzzle itself, I have to take into account this extra diagrams that comes in, right? You have the X contribution, and then you have the X and the photon interference contribution, right? So what we are saying here is delta A mu, which is the difference of the experiment, which could be either dispersion relation or lattice. This extra contribution should be explained by this extra added contribution that you are adding to the A mu itself, right? So whatever this extra term, the difference is, should be just these two diagrams and higher order. This is one test. The other test is the HVP test itself, where we are saying that if I just look at T plus C minus 2 hadrons, I have this, and this is competing against the photon, right? So if I just look at the AU HVP from lattice and the dispersion relation approach prediction, the difference between them should be given by this minus. So essentially, any new physics that you propose should have to uh, pass these two tests in order to explain all the discrepancies that are there. So what we have done is we have basically done this particular test. So what you see in the x-axis is the AU test, and this will take some time to explain all the slides. So let me go about. So here the 0 is the lattice point, and then the green band that you see here is the experimental value, and you can see that lattice is within 1 sigma of this value, right? And then you have the CMD3 experiment, which is also on the experimental value. So these two bands are doing good, right? This is the delta AMU test. And then one can go about delta AMU HVP, right? This is just the HVP test. In that also the 0 is the lattice, and the blue one is the CMD3 HVP prediction, which is also very close to that, right? But now if I take into account the theory initiated prediction, which is just the Babar and Chloe and not the CMD3, then you have some red band. And now in this setup of blue and red bands and green bands, I am going to put on populate my new physics models, the pink and the blue ones. And I will try to see, I will scan all the possible mass and the coupling values that can happen for this new physics model that can live on this plane, right? B is the gauge number, the new physics model that we're talking about. This is diagram number gauge goes on, and that's the dark photon.
Yes, two different scenarios.
Yes. So now we are looking at where does this new physics parameter space lie, and we saw that this region. So if I had any point in this black box here, that would mean that it will explain the theory initiative data which was lower, and it would also explain the delta mu which is exactly on the experimental value. So if I had any data point here in the new physics in this black box, I would have claimed that okay, I have a new physics model which passes both the test and explains the discrepancy that we have, which is pre-CMD era discrepancy. But if I have the CMD3 experimental result, then we are actually somewhere here, right? So if I forget about the red band, so there is no Babar and Chloe prediction, only the CMD3 result. So I am in this block. Here I see there is a lot of parameter space for nucleus to exist. But essentially, one can think that if CMD3 is correct, the first Occam's razor argument is that there is no new physics. And if there is any new physics, this will give you a bound on it, basically. If there are points on that, it will tell you that okay, if one needs more higher precision on your numbers to constrain the box over them. So that's what the conclusion would be that if I have a CMD3 result, the first and the foremost thing is to resolve it. There are two possibilities that can happen. Right? One where CMD3 is the actual result, and all the other results, Babar and Chloe, they actually reanalyze the data points and they figure out that there's some error and they come out with the CMD3 result. So that would mean this blue scenario, where you have now the next approach would be confirm the data that you have using other experiments, the muon experiment, the GeV experiment. And then if this is confirmed, basically what our previous plot is showing is that this will give you a new bounds on the new physics that can happen in your cell. And already there is a proposal for search for this big boson at the Babar for the Babar people.
But it's no longer there. We just reanalyze.
Exactly. Because if you look at the data points, we actually spoke to the Babar people and they said that they never really released their full unprocessed data. The plot that they have on there, or the table that they have on the papers, are already very much pre-processed and already model dependent. They have some models for the resonances, and based on that, the data is generated, it's published with the paper.
There's also the issue of Monte Carlos from which
Correct. Correct. So the Monte Carlo, there is one already a new physics approach. I think we got an email after our paper just last week from Luke Darwin in France. And their group, they were saying that there is certain baselines that by Monte Carlo generated for these experiments, and that has discrepancy between Babar, Chloe, and CMD3. So Monte Carlo, there's something called Focala generators that they have. That's the reason of the discrepancy between Babar and Chloe. So they are trying to resolve it and look at the data from a fresh perspective. Probably we will see new results coming in from Babar and Chloe very soon. So that is this scenario. And another one, so if suppose Babar and Chloe reanalyze the data, they say that there was nothing wrong in it. We had, and CMD3 comes up with some that they had something wrong, and that's the reason they are they had a higher value. And then there is obviously these two scenarios that we looked at, the new physics scenarios. They really don't have any parameter space to live on. Then, in that case, the puzzle still holds, right? Because simultaneously the AMU test and the AMU HVP test are not getting satisfied by the new physics criteria. And anyways, what's there to remain is multi-hadronic states on the lattice are going to predict more precise results from lattice calculation. And this is coming up in all different areas of lattice. From recently we had a paper with B2K star, B2K bar, B2 pi bar. And that also, with the help of multi-hadron physics, has a sub-percent error. So that's the final output of my talk. That things are getting murkier, but these things can be resolved by reciprocal collaborations. But at least from the lattice perspective, multi-hadronic states are here to stay for precision physics. And also, there is a R ratio calculation that is happening from lattice itself that involves an inverse problem of solving getting the scattering cross section from the AMU-HVP, which is basically inverting the integral and taking the lattice section for AMU-HVP and then inverting the integral to get the sigma. So that is there is only one result from the ETMC collaboration recently, where using some inverse Laplace methods and smearing kernels, they have a R ratio prediction. Obviously, it doesn't have all the nice features that one expects, which is the rho and the omega, but they have a very smeared result for the R ratio. And yeah.
So one question is B chosen is that the predicted mass range for this proposal because power is limited.
Yeah. So we are only looking at sub 1 GeV regime.
Sub 1 GeV means less than 1 GeV.
Less than 1 GeV. Because I know that my AMU test is most sensitive to any new physics happening from 100 MeV to 1 GeV, right? All the because there is so you see this 3s, the denominator. So there is already a reference. It's S square using group. So that basically says that any new physics from the higher than 1 GeV is not going to affect much AU HVP. So whatever new physics that has to contribute to this integral has to come from below 1 GeV. Where
There's also two different measurements of alpha electromagnetism.
yes,
There is a median else, both from France. If
Yes.
you don't agree with each other, what is its impact on?
that is delta alpha. This is delta.
No, it is shown that the most important contribution is the QE.
Yes.
So there, if you use these two separate different values of alpha,
Yes.
what is the uncertainty that you get from that? In your very first slide,
Ah.
when you plug in the value of
Yes.
when you plug in the value of alpha, you get that number.
Yes.
So there are these two different determinations of
Alpha.
QE in the constant limit
I see.
from two different atomic physics experiments.
They have an inconsistency.
They have an inconsistency, and both of them claim extremely small uncertainties and do not agree with each other like several sigmas, 7, 8, 9, 6.
I see.
Of course, you're immediately going to say that these are
Alpha Q.
that these are the underestimated experimental concepts.
Yeah.
Even the demons to experiment, because
Yes.
experimentalists claim that they have but who knows? It's probably something sitting in the one cloud.
But that's completely different experiment. E plus E minus hadrons.
Yeah, but even these guys, if they extract their data, they're bigger than all that.
Yes.
Uh,
Bigger than that.
there must be some because they, of course, they would say that they have 70 parameters that they model it very well.
Yeah, because they have a magic angle that they have to estimate. It cancels two effects. Give you.
Yes. Yeah, that's to kill the uncertainty.
Yes.
No, but when is their final data expected to run for?
I think it's 2025.
It's already 2025.
Just a few days, I think. Probably sometime later.
Latest.
Yeah. So I think for the white paper, the deadline is 25th January.
Which white paper?
The next one.
This one, huh? The next
Yeah.
series.
The next one in the series.
Thanks.
Yeah.
How does this compare this value of alpha? How does it compare with the value that is determined from the integer polynomial effect? Because that is now supposed to be
The most.
the standard for, and that is a very nice extreme low energy limit.
This is the QED contribution.
Yeah, just for QED. So I think were you asking about just the first stuff?
Yeah.
So that's why the integer polynomial effect is now supposed to give a
Yeah.
standard for alpha.
But that will also affect the alpha. I mean, that is also going to affect A electron.
No, so therefore any deviation
Yeah.
that you measure will then be sign of corrections.
Yes. But
Right,
anything
so
that
you
has
can
to
turn
be
it around and search for.
correct. And if it is determined at this uncertainty of 0.001 parts per million, then I think it will.
I'm sure the white paper will have a section.
Yeah.
Yes. I mean, but I mean, whatever alpha that we use, it has to have a certain uncertainty which has to, because that's where this number is coming from. So if you have an alpha s which is more precise, then this will go down even further. But I think the bigger,
I have no idea. I have no memory whether it is more precise or less precise than this. I only thought of it because it is integer
I can look
polynomial
into
effect
it.
is now used as a standard.
Integer quantum knowledge.
Yeah.
For determining alpha.
For yeah. They used to have from Josephson effect also.
Is that right? What? How do you do it?
I don't know. These are the various different sources for.
But one can think of is probably there are this regime that
This is the electric charge.
from lattice point of view, one can think of this was a very nice result which was shown that where the lattice coming can come into picture. Where this particular integral, where everything is finite but can be computed from the lattice directly from first principles. So maybe if we can figure out more such a where there could be non-quadratic coming in, especially I think in the CP violation lattice, it still has not reached that precision for CP violation. So that is one calculation probably already underway by different collaborations for the CP violation from lattice calculation.
And you take assistant breaking also into account. Like the up and down curves don't have the same.
Yeah. So that has been taken into account in the separate calculation. So where you do n equal to 1 plus 1, you look at how much it changes the result.
Okay, so it was just as a cross check. I mean,
Just as a cross check. So one can estimate the uncertainty that can come up because of assistant breaking.
and what's the answer? How much is it as a percent or?
I think I have number. Let me check. So this is 0.1%.
Oh, very small. So the contribution from the heavier curves is greater than
Yes. It's too big. is much lower.
Does it, I mean, does it contribute to the other thing, the weak and the electromagnetic? Well, like I think this MU you split it into three contributions: right? Electromagnetic, weak, and hadronic.
And QED.
QED being electromagnetic.
Yes.
So I'm guessing in hadronic it's 0.1%, but it's higher in the other two maybe.
So here you won't have any isospin breaking.
Oh,
Only in QCD you will have isospin breaking.
We can hang the speaker and then continue to.
that's all. Yeah, yeah, yeah. Okay, thank you very much.
Yes. The resonance. Yes.
Yeah.
Yes. Yes. You are considering for this particular approach all the different. Well, if you look at their numbers, they would have numbers per channel. Contributions per factor. Yes. Yes. Okay. Yes. Oh. What are these ideas? So we're just starting. So you're interested in the lattice calculation?
I think it's just, I mean, it's being a theory about this.
Oh, okay.
Yeah. This, these people can start.
Oh.
So he's special. He's now 40.
So you're computing things.
Yeah. And he